No. Oh, अच्छा. You camera? Camera on. Okay. Very good. Coming deeper. Camera on. Okay. Minimize and full screen. But where did that bar go? Disconnecting. Am I audible? My phone. Am I audible?
Hello.
Hello. Hello.
Hello. Hello. Yes. Right. Yeah. Yes. Yes.
Screen is shared.
Yes. Yes. But nobody can change. Means even I can go back to you.
उन्होंने ऐसा सेटिंग किया है कि you continue.
So if you have any problem, you can post the same thing in the chat. Okay. I think that will be better. Now let's start. So yesterday we So yesterday we reached up to the completion of the valence bond treatment of the coordination with bonding. Today we will start the crystal field theory. So in crystal field theory, we consider the metal ions and the ligands are completely ionic charges, where metal ions consist of the positive charge and the ligands are consist of the negative charges, and the force is purely electrostatic in nature. By considering the components in this way, it was very much helpful in predicting several physical and chemical properties like magnetic moments or color of the complexes. So in order to understand the before we move towards the crystal field theory, we must have a very basic idea or the concept about the different d orbitals present in the central metal ion. This shows the central metal ion where it is a typical octahedral geometry, where in this these octahedral are considered, where it is present. There is an equatorial plane consisting of these four ligands, basal ligands, along the x and y axis, and then axial ligands are available in the z axis. So we can think about this. Now we understand that there are 5d orbitals, out of which the 3d orbitals, which is shown in the lower panel, they are dxj, dxj, dyz, and dxy. In these three, the dxz, yz, xy, it has particular meaning. This is, you can say, actually the plane in which they are placed. Dxz or zx orbital means the all the four lobes are placed in the xz plane of the xz plane in a cubic arrangement. Similarly, yz and xy represents their orientation in the corresponding plane. But their orientation of the lobes is in between the axis, not along the axis, in between the corresponding axis. That means in zx, the lobes are oriented in between the x-axis and z-axis. Next, there are two other different types of lobes, the different types of orbitals, which are directed along the axis. One is dz square, this one, where the dz square orbital is this one, which is oriented along the z-axis, and there is a ring in between at the central point, which is at the nodal point. There is a ring, and their symmetry is like this. If this is plus, then the central ring will have a minus charge. And but this is oriented along z-axis. Similarly, the dx square y square orbitals are oriented along the x and y orbital. If this is the x-axis, then this will be the y-axis. Okay. Therefore, if we again come back to the octahedral geometry shown in the first box, we can understand that all the 6 ligands are placed with the or forming bond with the two orbitals. One is dz square, that is this bond that will be like this. This is the dz square orbital, okay, and the other bond is 4 bonds are along the x square x square y square orbital. Therefore, they have been differentiated in 2 sets. One is T2G set, the lower one, which is practically non-participating in the bond formation, and another set, the upper one, is called the EG set. Okay, so this EG set and this T2G set. Now again we come back to the crystal field theory. When we consider a particular electronic configuration, we know that there are 5d orbitals. These 5d orbitals under a crystal field, it experiences an spherical field. In a spherical field, its energy is increased. Now here one term you must try to understand. When all the orbitals have the same energy, they are called degenerate set of orbitals. So this is a degenerate set of orbitals under the spherical field. That also gives a degenerate set of orbitals. Okay, but when this is placed under the crystal field, suppose we are considering an octahedral geometry, then the degeneracy of the set of orbitals are lost, and they are divided or split into 2 different degenerate sets. One is this one, another is this one. So the lower one is T2G set and the upper one is the EG set. Now, the splitting of the orbital takes place in such a way to maintain the barycenter. Barycenter means the energy of the ground state Okay, so in the spherical field, what was the energy that along that line the barycenter is maintained? Three orbitals, these three orbitals, lower panel, xz, yz, and xy, these three orbitals, they are lowered down by certain amount of energy or stabilized. But to maintain the barycenter, the other two orbitals, that is the EG set, they are increased by certain amount of energy. Now the decrease, total decrease and total increase, they will nullify each other. So we consider this as -4 dq. That means each orbital gives a stability of -4 dq, whereas each EG orbital will provide a destabilization of +6 dq, so that the resultant energy becomes 0. That means which is the energy of this spherical field, that remains same when they are completely filled for a D10 electronic configuration or a half-filled D5 electronic configuration. So this is the case with an octahedral geometry. Now, in an octahedral geometry, now the question arises that how these T2G and EG different sets, they have been separated into different energies. That depends when we consider the orientation of the orbitals. When we consider the orientation of the orbitals, then the EG set two orbitals, dz square and dx square y square, they are directly in touch with the ligand. So the interelectronic repulsion between these two orbitals, between the metal orbital and the ligand orbital, they can increase the energy of these orbitals. So they are increased. But you will have to maintain the barycenter. That's why the other three orbitals, which are also non-participating in the bond formation in this way, they are stabilized by certain amount of energy, that is -4 dq for each orbital. So this is the very simple case of octahedral geometry. Now, this is the sample has been shown for the octahedral geometry. Now, if your geometry is tetrahedral one. So if the geometry a tetrahedral one, a tetrahedral geometry can be best convinced by considering a cube. So if we understand a cube, then place at the corners of the opposite diagonals of opposite faces the lattice points. So I am writing here an L, another L. So this is along the this diagonal. So the other diagonal, opposite face diagonal, will be this one, and at the center there will be the metal. Now you can connect them by certain bonds so that okay, now it shows that it is nothing but a tetrahedral. So in this tetrahedral, if I now want to understand the exact geometry over the exact orientation of the orbitals, then we will find that the metal is at the center. So this is the Z orbital, and say this is the X orbital, and say this is the Y orbital. Now you see no orbitals, no ligands are oriented along the X, Y, or Z axis. That means in X, we know that in X, Y, and Z axis, these two, the T2G, the EG set of orbitals are present, but no, the bonding are formed not along these orbitals. Rather, they are forming along the other set of orbitals, that is the T2G set of orbitals. Forming the other set of orbitals. So the energy is just reversed in comparison to the octahedral one. So if I take it for the say the spherical field, then it will be now the lower is -6 dq and the upper part is +4 dq, so that the barycenter is again maintained. So I think now you have understood about the orientation of the 5d orbitals and why do the splitting pattern of the tetrahedral and the octahedral is opposite? Okay, now we will show you the gradual shifting of the tetrahedral from the octahedral to tetragonal distortion to square planar. So it shows the normal octahedral splitting. Normal octahedral splitting means we are presenting it in this way. Suppose if I take a molecules with the formula say NH3 then we'll see that all the bonds are equal. But that means rather I am presenting these. Just 1 minute. ML6 with all the axial and equatorial bond distance equal. Now the ligand field is changed by changing the L or by changing the metal. That means if you shift from one metal to another metal, the situation may arise a special case which leads to a particular distortion known as Jahn-Teller distortion. Will come later, so that the axial bonds are either elongated or compressed. So in the next case, what happens when the axial, say the axial bonds are, in this case, we are considering they are elongated. A stretching takes place. So if the stretching takes place, then the bonds which are present along the z axis, they will be elongated, and the electrons present over there, they will face less amount of electronic repulsion, causing a splitting. So there are three orbitals, xz, yz, and xy, and here are two orbitals, z square, x square, y square. Now along z axis they become stabilized, so they will be splitted into two, and xz yz will be stabilized and xy will be destabilized again to maintain the barycenter. So it becomes like this. Here this is z square, this is x square, y square. So we get a structure like this. You see, the axial bond are now larger than the equatorial bonds in the second step. Again, we apply further stretching so that we give them so stretch so that these ML bonds are broken. So if that breaks, then what happens? There will be nothing along dz square orbital, and dz square will be further stabilized. So there will be change in the position of the orbitals. It will be like this. Dz square will come here and xy will go up, and all the other xy containing orbital, they will be increased in energy because now everything is in the xy plane and xy along the xy axis. So the Again, dxz, yz will be further stabilized. That will be like this. So what do we get here? We get a totally new geometry, which is square planar. Okay, which is square planar geometry. I'm M, L, 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 L. Here also M is at the central, L, 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 and L, 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 M. So the difference between the first, second, and third is that in the first, all the axial and equatorial ML bond distance are equal. In the second, that is called tetragonally distorted geometry, the axial bond ML bond distance are larger than the equatorial bond distance. And thirdly, the final one, there is no axial bonds, only the equatorial bonds, and they have the same distances. So this is how the d orbitals get splitted under the influence of a tetragonal field, and further with the extreme tetragonal field, it becomes the square planar one. So here I have fixed the table here at the bottom. You can study this one. That will be very helpful to calculate the CFSE. That is crystal field stabilization energy, CFSE. So finding the crystal field stabilization energy is a very important step. Just 1 minute. Oh. So we have shown here two different geometries and the corresponding splitting. Okay. So here you see on the left side there is tetrahedral splitting, and on the right side there is octahedral splitting. And as we know that right now we will put the calculate the different number of electrons feeding. Say for the, just see the table at the top at the bottom left, for the D1 electronic configuration. So for the case of octahedral one, I am putting the electron over there. So 1 electron means it is how much? For this is, we know this is 4 dq for the octahedral. So this will be minus 4 dq. So the first one. For the second one with d2 electronic d2 electronic. So this is, so this will become minus 8 d cube. Minus 8 d cube. For the third d3 minus 12 d cube. Okay, in this way it will be filled up. Now come to the, there are two kinds of spin. One is low spin and another is high spin. For the high spin electronic configuration, that means all the orbitals are fast filled That means the EG set of orbitals after the filling of these 3 electrons, the next 4th electron will move to the EG orbital. EG set of orbitals, the electrons goes there. So for that, it will be -12 plus 6. That is equal to -6 dq. So you see for the D4, for the D4, D4 it is there -6 dq. Okay, for the high spin. But if it is low spin, then it will, instead of moving there, the electron will enter here. So now it will become -16 dq. Okay, this one -16 dq. But at the cost of pairing energy. You see, one of the electron is paired up. So pairing certain or electronic orbital, that is an energy required process that requires certain amount of energy, and that will be lowered down or subtracted from the crystal field stabilization energy. So this becomes 12 dq, but at the cost of one pairing energy. The second electron, if it is low spin, it will go here. Okay, but if it is high spin, then it will go there. That is for the D5 electronic configuration. You see, for the high spin D5, it will be like this. For the high spin D5, it will be 0. 10 dq is 0 as observed for the here. Here it is 10 dq is 0. So in this way, the 6th electron can enter here, then 7th, 8th, in that way. But for the low spin up to D6, all these 3 will first fill up, then the 7th will go to the top. So in this way, the CFEC is calculated. On the tetrahedral splitting, we know that it is just reverse that of the T2 set, T2 and E set. Okay, one one important fact is that when you see, we represent this is by T2G and EG, and we represent when we consider the tetrahedral, we represent the sets of the degenerate orbitals as T2 and E. This G has certain symmetry characteristics. G means Girardet. Okay, so that comes from the symmetry consideration. As in octahedral geometry, that is symmetric in nature, so the G terms come, but the tetrahedral geometry, it is not symmetric, so the G terms does not come. In the these are known as the Mulliken term symbols. In these Mulliken term symbols, the G terms doesn't appear. So these T2 and E, they are splitted in this way, and accordingly you can fill up. For this is -6 for the lower one and +4 for the upper one, and you can calculate the same yourself. From here, I will try to continue the magnetic moment part, which is not. So I think you are now now you have sufficient idea about calculating the crystal field stabilization energy. Next, actually the crystal field theory was very much helpful in predicting the magnetic moments for the majority of the electronic configurations. The magnetic moment is usually considered for the transition metals. The magnetic moment mu is given by the Bose-Stoner equation. This equation is known as mu is equal to √n into n plus 2, where n is the number of unpaired electron. Where n is the number of unpaired electron. Okay, so from any electronic configuration, now you can understand. Say if I take D1, it will be √1 into 3, so 1.73. Similarly, for D1 to D3, there is no difference in high spin or low spin. So for all of them will be same. So if I take D3, that will be root over 3 into 5 equal to 3.992. But for the D4, if it is D4 low spin. D4 low spin means this is the electronic configuration. D4 low spin, forget about these two. D4 low spin, there are 2 unpaired electrons, so it will be 2 into 4 is equal to 2.9. But D4 high spin, there are 4 unpaired electrons, so it is root over 24. Okay. Similarly, for D5, it has a D5 high spin, it is root over 35. But for D5 low spin, it will be 1 unpaired electron, so root over 1 into 3, that is 1.73. So in this way, you can directly calculate the number of unpaired electrons by just feeding the electrons in the corresponding orbitals and directly calculate from this equation. But you must be very sure about the splitting pattern. For that, what you need to do? For that, you need to first understand whether it is a tetrahedral or an octahedral geometry. How to identify that? For octahedral, there will be 6 ligands. For tetrahedral, there will be 4 ligands. For tetrahedral, although there are the other possibility with the 4 coordinate ligands, that is the square planar. Okay, so but for square planar, the examples are very limited. For square planar, they are basically all the square planar with usually they do not have unpaired electrons. Basically, for the D8 electronic system, they do not have any unpaired electrons and they are diamagnetic in nature. So this is how I think you will have questions to determine the magnetic moment with this simple equation. But in the later on, I will also emphasize on some other equations for the lanthanides and actinides. Okay, so I have covered the magnetic moment part here for the transition metals. Again, I am asking you, if you have any doubt, please post it in the chat box. Next, Next, we will start with the spinel. Spinel is a beautiful inorganic mixed metal salts of the general formula AB2O4, where A has charge 2 plus, A has 2 plus charge and B has 3 plus charge. Now their arrangement shows that A2 plus occupies the 1/8 of tetrahedral holes of a face-centered cubic crystal of an FCC lattice, and B3 plus occupies the half of octahedral holes in a FCC lattice. So from there, it has the that means A will go to the tetrahedral hole and B will go to the octahedral hole. So A B2O4, I can say that when it goes to tetrahedral and it goes to octahedral hole, then it is a normal spinel. But there is another spinel structure which of the formula BABO4, where B goes to the tetrahedral hole and AB goes to the octahedral hole. This is called inverse spinel. So normal spinel and inverse spinel, 2 types of spinels are there. Here I have mentioned the tetrahedral and octahedral holes, and as it shows So before that, we must have an idea about these octahedral and tetrahedral holes of void spaces. Bottom there, it has been prefixed to FCC lattice. Now let's try to understand about these holes. So if I draw okay, so you can see this is how a FCC lattice is seen. That is basically a sodium chloride type of structure where each of the lattice points are covered by sodium, and these points, these intermediate points, they are occupied by the chlorides. So in this structure, if you see it very carefully, then you can observe that if I think about the a cube, this whole cube is composed of 8 small cubes. 8 small cubes, 4 at the bottom and 4 at the upper level. Out of 4, in each case, 2 at the front side, 2 at the back sides. Okay, 2 at the front side and 2 at the back sides. Now, if I try to understand that, then I see that this one, I am trying to connect these points. This one. Don't consider this one because this is at the back side cube. So you see, there are 4 lattice points here. I can number them as 1, 2, 3, 4. And it is a tetrahedron which does not have a central lattice point. So this is a central point which is missing with any lattice point from where, but if you place one point there, then a complete tetrahedron will be formed. So this point, this is the void point, or this is the void or the hole, and it is placed at the center of a tetrahedron. That's why it is a tetrahedral hole. Now each cube has 8 such small cubes, so there are total 8 such tetrahedral holes. Now in the spinel structure, the dipositive cation, that occupies the 1/8 of this tetrahedral hole. So out in the whole lattice of in the unit cell of the FCC lattice, one of the tetrahedral hole is occupied by A. I think now it is clear that how the tetrahedral holes arise and how where the A2 dipositive cation goes. Next, let's try to understand the octahedral hole. So if you try to understand the octahedral hole, then first of all, you can consider this one. You can consider the center. You can consider the center of the cube, because it is surrounded by, you can say, 6 lattice points which are placed in an octahedral way. You see, what is this? This is an octahedral. Okay, that yellow point is a octahedral point. Octahedral center where there is no lattice point. So this is the octahedral hole. And FCC unit cell, not only this central octahedral hole, there are several other octahedral holes. Several other octahedral holes can be convinced by simple consideration of a. If you extend these things, I am writing one face here and extending to the other sides. So there will be again a lattice points like this here. One lattice point will be here. One lattice point you will also get it here. So now what is this? This is okay. It's slide little bit different, otherwise both of them will be same. So these, and these. So again, you see there is a point which is this central point. There is again an octahedral hole. Now, one such cube has 12 such sides, and each side had one octahedral cube, one octahedral void space. But this octahedral void space is shared by 4 such cubes, 2 bottom, 2 at top. So practical contribution of each such cube is 1/4. So total contribution is total. How many sides are there? 12. So 12. Sorry. So total octahedral cubes will be 12 into 1/4 plus this central one. This is entirely shared by this lattice itself. So plus 1 is equal to how many? What is it? 4. How many number of tripositive cations are there? There are 2 tripositive cations. So it is said that B3 plus half of the octahedral holes are occupied. Okay, there are total 4 octahedral holes and 2 B3 plus. So half of the octahedral holes are occupied by B3 plus cation. Now, what we are saying all these things, because just in the prior section we have seen the different splitting pattern of tetrahedral and octahedral geometry. Now it depends whether. Now also we see that here A and B are going to either octahedral or tetrahedral lattice sites. So crystal sites. So it depends depending upon the electronic configuration. So as we okay, so depending upon the electronic configuration, we can now measure on moving to which side. On moving to which side it will have more crystal field stabilization energy, then it will go there. And here also you see the amount of splitting of octahedral splitting or octahedral CFSE is larger than the tetrahedral CFSE. And this is given by the relation delta OH is equal to that is 9/4 of delta TD. that is more than double octahedral splitting, octahedral crystal field stabilization energy. So if a particular electronic configuration gains more CFSE on moving to octahedral holes, then it will definitely go to that octahedral side. Okay, so from here we can now analyze that for the general formula AB2 A4, whether it will adapt a normal spinal structure or a inverse spinal structure, that depends upon that this we need to consider the electronic configuration of the corresponding metal ions. Okay, so by consideration of that, then we can understand what it will adopt. Now the one question is that one common phenomena is that if some metal ion has a D5 electronic configuration, then it doesn't matter if the B3 plus has a D5 electronic configuration, then it doesn't matter where it moves, whether it is tetrahedral hole or octahedral hole. So it has been observed that in those cases, it may adapt the inverse spinal structure with the D5 electronic configuration. And in the rest of the cases, then we need to consider the respective crystal field stabilization energy. I think there is the table here as discussed over there. And here one more lambda is introduced, where lambda is the occupancy factor of the B plus 3 in tetrahedral hole. You see, B plus 3 will move to the tetrahedral hole only in case of inverse. Okay, B plus 3 will move to the tetrahedral hole only in case of tetrahedral, only in case of inverse spinal. Here in the normal spinal, all the B plus 3 is in the octahedral hole. So the value of lambda, maximum value might be 0.5. And the minimum value for lambda is 0, which is for the normal spinal. So lambda value is 0 for lambda is equal to 0 for normal spinal, and lambda is equal to 0.5 for inverse spinal. So this is the limit within 0 to 0.5. If the lambda value varies, then they will be adapt this. From the table, you see with the D5 electronic configuration here, it is showing that 0.5, 0.45, 0.5, 0.5, 0.5, 0.5, 0.5. That means this combination Mg Fe2O3, Mn Fe2O3. Okay, for Mn, if this is not exactly not going to the inverse structure, but for Fe3O4, in which Fe2 that is Fe2 Fe2O3O4, this will have inverse 0.5. Similarly, cobalt Fe2O4, cobalt 2 and Fe3 that will also have inverse. Okay, or copper Fe2O3, Fe2O4 that will also have inverse structure. Okay. Okay, so I think today's time is we can complete it here. The spinal part is finished here. Now I am expecting some questions from you. You can send this in the chat box, or you can ask, or you can mail, send us the email. Okay, we will address those questions. and you can find it from the website from SUBNASKAR at oh sorry, not this one. SUBHENDU at bitmesra.ac.in. You can send email to this. Okay, then we will address those questions now. So we can go to exit. वहाँ